The last series of climate science ideas born in only at the University of the Max Planck Institute at the Arion Center. And I will present today some of the developments and results that we obtained in the early 2000s, so about 20 years ago or so. I was much younger. You will see then later some pictures as well. And the topic is a little bit methodological, as the title says. It's about statistics, about climate reconstructions, about pseudo-proxies. And I hope that won't be very boring for you, for those of you that are not interested in statistics, but it will contain some lessons also in other areas of climate research. So just don't disconnect thinking that it was only about paleoclimate. As I said, I hope that it will be contain some insights and lessons for everyone. So I'm, as Nerka said, I'm working at the Helmholtz Center, Arion. That 2 or 3 years ago was used to be named Helmholtz Zentrum Geesthacht, and before that was the GKSS Research Center. But my name remained the same. So hopefully, and it will also remain the same as well. So my name is Eduardo Zorita. I'm working at the Arion Center. So that was the corporate announcements. Let me just start motivating my talk. It will be based, as I said, in the problem of paleoclimate reconstructions. And at that time, we were motivated by this hockey stick reconstruction that is very well known. It's a reconstruction of the Northern Hemisphere temperature of the past 1,000 years, based on proxy data. I will explain a little bit what proxy data are and how they are dated and calibrated, because they're a central question in the talk. And you can see that the evolution of temperatures is over the past millennium, very flat. You have some slightly warm temperatures around 1,000 years ago. It is called the medieval climate anomaly. Then colder temperatures during the Little Ice Age around 1600, and then the very rapid recent warming caused by, of course, by greenhouse gases. This graph was very controversial at that time. For those of you that perhaps are not aware of that debate, 15 or 20 years ago, that was one of the main iconic figures used in the IPCC report to demonstrate or to prove the influence of anthropogenic greenhouse gases on climate. And we will see perhaps later a little bit that that was not a very clever strategy, that is not completely correct, and that was also one of the reasons for the controversy. There are books by one of the authors of the reconstruction, by Michael Mann, telling all the story of these debates and the controversies and the arguments that were exchanged at that time. Some of them were correct, some of them were not correct, as usual in life. But that will be the focus of our, let's say, our talk in the next 30 minutes. But as I said, it's just, let's say, a motive to look into statistical models in more detail. So usually in statistical models, we have a collection of data, and we try to derive then information and interpret those data, sometimes with the help of a statistical model. The problem is that when we don't have enough data, or when we already have in mind something that we want to prove, the danger is that we can get into the overconfidence. That's trying to derive a lot of conclusions that perhaps are not supported by the evidence that we have, although those conclusions may be true or not. But that's, I would say, a usual case in statistical analysis. Also very usual in climate research, in which the sample size is very small, the observational record, and we try to prove a lot of ideas that we have. Now we'll get into more detail about the technical aspects of these problems. And for those of you that perhaps are not related or not familiar with paleoclimate, I will explain a little bit what climate proxies are. So climate proxies are indirect indicators of past climate. temperature and precipitation. So they are biological or geochemical systems that record the past environmental conditions, temperature or precipitation. And better known are tree rings, of course, but we have also lake sediments in which we can analyze remnant pollen and pollen assemblages of the past. We have also historical documents in which historians can derive past climate conditions of the past and try to calibrate them to interpret temperature, precipitation, or extreme events. But tree rings will be the focus of our research, of our talk. And the reason is that they have a very good advantage. They can be very well dated to the year, so they can be exactly dated with almost no uncertainties. And they provide mostly information about temperature, which is a very nice parameter. It is the main climate parameter. So what can we do with tree rings? Usually we have information from living trees. And we core stem of the tree, something like that, a half a meter core, and we see the tree rings that have formed every year. So the assumption is that in years in which the temperature or precipitation has been favorable for growth, then the ring will be wider, and in years that have been cold or dry, the ring will be, the growth will be smaller, will be narrow. So we have information about past climates. But a living tree lives perhaps 100 years. So we need information about 1,000, 2,000 years. So we can go also to fossil trees, so trees that are already dead, or that stay in the landscape, or they are part of buildings. And we can also extract core of them and identify all those tree rings. But in the case of a tree that has died in the past, we don't know exactly the date. It's a floating concept, right? In time, we cannot fix the date in which the tree was born exactly. So what we do is we try to find periods of overlap between the living tree and the dead tree. And when we see these barcodes that we get in the supermarket that match exactly the succession, for instance, 10 or 20, 30 years that it's, the barcode matches, then we can date the dead tree. We can see, okay, the end of the dead segment coincides with 1910. And then we can go back in time in this way and reconstruct, let's say, the temperature, theoretically, over the past 2,000 years, something. Now the problem is, how can we interpret those data, clearing data? We only have centimeters. We have, 2 centimeters, 3 centimeters, 1 centimeter. We have to translate it to temperature. And the way to do it is by statistical calculation. We get now into the statistical models. So we have a period of overlap, mostly in the 20th century, between observations and the proxy data. And we try to establish a statistical link between the tree ring variations and temperature variations. This looks very simple, but now it really gets tricky. And what I'm going to say in the next few slides probably will be surprising for some of you. It is a simple linear regression problem, and here we already have, well, we have to be really careful. One way to calibrate a proxy time series is just by building this statistical model between temperature, which is proportional to the tree ring variations. And we estimate the regression parameter A, right? This is one possibility. We have, however, another possibility. We can apply an inverse regression. We can set the statistical model as a proxy is proportional to the temperature. And we estimate now the proportionality coefficient P. And we can then reconstruct the temperature by inverting the equation. Sorry if that's a little bit distorted, but it's read here 1 over B multiplied by. Okay, then we have two methods to calibrate the same time series. The problem is that A does not equal to 1. It's different. So what is the real? What's the real parameter? What is the real regression? Actually, we have now to look physically, to think physically, what is the independent variable and what is the dependent variable, which is the variable that contains no noise and which is the variable that contains noise. And in this case, actually the true model, the physically true model is the second one. The proxy is reacting to temperature. And on top of that, there are some other biological processes that are not related to temperature and are encapsulated by the noise. So the first model, statistical model, is wrong. It's basically wrong. And that leads to a wrong estimation of the proportionality constant. Ironically, the first model is the model that is used by the endocrinologists to reconstruct past climate and has been used for decades. Although actually the statisticians knew that, and they would say this is wrong. Nevertheless, climate research keep churning on using the wrong model over several decades. This is a lesson for us, because we usually look down to statisticians and say, oh, mathematicians model. So they don't know actually what we are doing. That's the right thing. But it's actually the other way around. We don't know many things about statistics and mathematics in general, and we are a little bit arrogant about that. That's one of the lessons apart from Pablo. Okay, we can now illustrate this problem in this still regression between just two variables in this paper that was published in 1990, linear regression in astronomy, and it illustrates the problem that I mentioned. When we have just two variables, x and y, one is the predictor, one is the predictant, we don't know which one. And we have some measurements, and we try to estimate the linear slope that goes through the measurements in the best way. The problem is to define which is the best way. One, minimize the distance in this direction, in which time the predictant will be x. We can minimize the distance in the y direction. In that case, the predictant will be y. Or we can minimize the predictant perpendicular to the line. So we have many flavors of linear regression. And I think, I'm afraid that in climate research, we're just of one. We go to the Python routine, we have two data sets, X, Y, go to the Python routine or R routine, calculate for me, please, the regression coefficient, and that is. There are many flavors of linear regression, and all of them are different. This is, for instance, an example of the same data set in which we try to estimate the regression slope with all these approaches, and we get clearly different results. That means that when we apply these ideas to estimating past climate or to estimating any other variables that we need to estimate that have not been observed, we have to decide which model is best. Is the first question. Okay, now we move now into the application of paleoclimate. As I said, we were focusing on reconstructing the temperature over the past millennium. Just to have an idea how the climate may have looked like of this period, I've just plotted here the three main climate forcings. One, of course, is the greenhouse gas forcing that has increased dramatically in the last 150 years, something like that. We had also variations in the volcanic activity, so that's very important over the past millennium. And we see that, for instance, during the Little Ice Age, 1600, 1700, volcanism was very important and was very important for cold temperatures. And around the medieval warm climate anomaly 1000 years ago, it was very weak. So that also contributed to this warmer temperatures. And we have also solar variations that were at that time very uncertain. So the time evolution was certain to some extent, but the amplitude of variations were uncertain. Nevertheless, well, that gives a picture or explains a little bit how the evolution of temperatures may have looked. Now, with this idea in mind, Mike Mann and Ramon Bradley and Malcolm Hughes went on the first attempt to estimate the temperature fields, not only the mean temperature, but the temperature fields that will resolve over the Northern Hemisphere over the past 1,000 years. And they use a network of proxies, most of them tree rings. But this is the network that they used. As you can see, it doesn't cover the Northern Hemisphere by far. But, well, the idea was, can we use those to reconstruct the climate fields every year over the last 1,000 years. And they used, a statistical model, and now we get again into the details, that can be summarized in this form. So they computed first the principal components of all the proxy series that they had, and then kept only 10 or 15. Then they said, okay, the reconstructed temperature field will be a linear combination of these time series, and we have to estimate the age, which now are the regression slopes, but there's a field. Now it's not just a parameter, it's a field of the whole world. And so this model is, if you look at it, actually very reasonable, because this separation of the temperature field in stable patterns and time series is what you do when you compute a principal component analysis of the temperature itself. What they did only, they replaced the principal components of temperature by the principal components of the proxies. That's what they did. So the model, the statistical approach looks, well, very, very reasonable at that time. Even now, say, okay, this has to work. This is very, very, there's no reason why it shouldn't. So we have to estimate the fields by minimizing the deviations from the reconstructions and observations in a period. This is the standard procedure. There were some assumptions hidden in that proved to be actually fatal. Although the model looks very reasonable, there are two things that actually, as I said, disproved or actually made that this model couldn't. One is that they computed the principal components over the last 100 years only. Every one of us would say, well, why not? I mean, there's nothing wrong in that choice. That apparently is harmless, but it proves really fatal. We will see later. And now in this model, the temperature is the predicted. And as we said before at the beginning, this is the direct regression between two time series, and not related in that way. The relation is inverse. So we can already assume, or perhaps be afraid, that the model will not work. Okay, then we'll look at the details of this. And how can we test this method? So the conclusions that they obtained from this reconstruction was, as I said, that the temperature evolution was very flat before the 1900s. No effect of solar forcing and very little of volcanic forcing. That was already surprising at that time. But it has been confirmed later. So that conclusion was really true. Of course, you see a steep rise of after 1900 due to greenhouse gas warming. That's confirmed as well. And the 1 year was flagged as the warmest year in the past millennium, 1998. So the reconstruction was published in 1990. They concluded from this fact that, well, that it was a proof of anthropogenic climate change. And that was the skeptics and later latched on very, very, very strongly. Because if you look at a wider time scale, let's say the last 10,000 years, this is not the case. So there are years or periods in the mid-Holocene that probably were warmer than today. And immediately they pointed at that and say, well, the hockey stick thing is wrong. And the conclusion that there is an effect of greenhouse gases was already warm, only focusing on that last point that actually is not relevant. And we can see it we can dispute it, we can discard it very, very easily. So we sit here in this room and we turn the heating on. And now I'm climate skeptic and say, well, the heating has no effect because I was sitting in this room last July and it was much warmer. This is the logical reason that was attacking this point, which is actually illogical. It's absurd. But well, ironically, then there was an exchange between climate skeptics and let's say the IPCC mainstream based on that point. And people then started quarreling about temperature differences in the medieval climate anomaly of 0.1 degrees in the global. And they were calling, well, this is warmer by 1/10 of a degree or cooler, and that disproves the whole thing of greenhouse gas. Totally absurd, but well, that's the, let's say, the spirit of the time nowadays. Okay, now more scientifically, we decided, okay, let's test this method with synthetic data. And this is the story of pseudo-proxies. What are synthetic data? Well, imagine that we have some collection of data, and we have to fill the picture. It's a person guessing. Can we perhaps say with artificial intelligence, can we generate a new data point so that we can then test our reconstruction method? If that reconstruction method using these 3 persons produce a 4th person and see if that method only works. So we construct a virtual reality with new data points in which then we can say, okay, there's indeed a new person. That looks very similar to the other ones, but it's not the same. It's extracted from the same statistical distribution, from a similar statistical distribution. Okay, of course, this is a joke. So let's move forward. Now in reconstructing past climate from noisy data. It's a paper that was published in 2004. So the leading author was Hans Storch, of course. And we said, okay, let's try to test all the paraphernalia of this statistical method, which was a little bit complicated, had some assumptions hidden between. How can we do that? So, well, the idea is let's dive into a virtual reality in which we know everything. We know the past temperatures, we know the local temperatures of the proxies. We can apply this statistical method, pseudo-reconstruct the temperature and compare it with the true temperature that we know in that virtual. And the virtual reality that we chose was a climate model. Climate models not only, well, they produce a succession of climates as in reality. It's not reality, but it's a plausible reality. All the physical variables are related to each other as they are in reality as well. They are not perfect, a perfect exact image of reality, but this is something that is plausible. We only want a laboratory to test our method. So it's not very important that the model has deficiencies here and there. It's only that it's physically consistent as a laboratory. We go into the laboratory, change things, test methods, change boundary conditions, and then we see if the method is actually functional. So we used the OG model at that time, which is the ECAM-HOPE model, ECAM-4. And for this test, we had to produce 3 rings in that virtual reality. Climate models do not produce 3 rings. And the idea to produce the 2 rings was the construction of pseudo-proxies. An easy one is just to say, okay, the 3-ring variations is the temperature plus some noise that represents the biological and non-climatic evolution of variations of tree. That's one possibility. It's a very simple one. Now it gets more complicated. You can choose the noise white series, for instance. You can change the amplitude of that noise, and then you change the correlation between the temperature and the proxy, the relationship. If the noise is smaller, that link is stronger. So you can tune it to mimic the relationship between proxy and temperature that exists in reality. But also you can go to more complex noise modes. For instance, this is a long-term autoregressive series in which mimic, for instance, that the noise in the 3 rings can have long memory. For instance, if they have an infection, that infection will last for several years and will impair the growth of the tree over several years, not related to temperature. So there is a long memory in the noise, in the non-climatic noise. We can also add, for instance, precipitation. Some proxies are a mixture corresponding to a mixture of temperature and precipitation. Well, now you can imagine we can test all these possibilities. We can also reduce the network of proxies. because in 500 years ago, the availability of proxies was smaller. So we can test what impact has this reduction on the network. And this is one summary of the results. So here I show the simulated temperature by the climate model directly. So the black line. And all those colored lines are pseudo-reconstructions under different hypotheses. This is on the noise, the size of the network, etc. And you can see that all of them underestimate the past variations of the temperature. So that was an indication that the model was not actually capturing the whole full amplitude of variations. The reason was probably the switch between predictor and predictor. That was not good, because that underestimation occurs only for linear regression in between two variables. Well, we published that, and there was a, whoa, that cannot be true, that the method applied by Eichmann was could be not correct, and so on. Well, it was then confirmed by other groups as well, that actually that method tends to underestimate the variance by different amounts. Of course, you cannot know for sure, because you don't know how many noises in the proxies, etc., but you find a systematic underestimation of the temperature variations. So we also continued or progressed testing, as I said, with a dense network, sparse proxy network, or including some other types of proxies, long memory proxies, that not only autoregressive, but they have this first behavior, very, very long autocorrelation. And we also tested many other methods. So principal component regression that was at that time also used for climate reconstructions. For instance, composite plus scaling, that was one of the methods that were used. And they all shared the same characteristics. Again, here the black line was the temperature simulated by the model, and all of the lines were the pseudo-reconstructed temperature. So they all showed an underestimation. Now other groups latched on that idea and tried to find out why was that the case. And here I showed just a summary of a paper by Gertbürger and Ulrich Kubas. Kubas was at that time already in Berlin, but he was a very long employee of the Max Planck Institute, a scientist. And what they tested was variance of the original statistical model. So there were some assumptions that I mentioned before. So they said, okay, what happens if we modify these assumptions somehow, a little bit? So they come up with 64 plausible variants of the Mann, Bradley, and Hughes reconstruction methods. And they found that the spread of the results was very high. So actually, the hockey stick that they presented was one possibility, but they could have come with many others. All of them, however, would underrepresent the true variations. And now I'm coming almost to the end of my talk. I will also show another point that was critical for them. So I mentioned it at the beginning. It was this calculation of the principal components only using a partial time period. I think there's a lesson also for other statistical models. So, and this was actually, we missed that. I have confessed that when I programmed this reconstruction method, I missed that problem completely. But there was another, well, two persons, Stephen McIntyre and McCritic, that were very, very much criticized. Well, Stephen McIntyre worked for the Northwest Explorations for Mining Company, so you can imagine an employee of a mining company publishing in climate research and criticizing the hockey stick. But that was climate war, of course, as Mike said. And they said, well, look, here there is an aspect of the method that actually makes it impossible for it to work. And well, the reaction was, well, this cannot be true. I mean, you are skeptic, you are biased, which may have been true, probably, but that didn't take any weight on the argument, the scientific argument. And the scientific argument was correct. What they said was the following. So the proxy time series have long memory, as the tree rings have. And the principal vectors are estimated using only the calibration period. Then even random series will produce a hockey stick. And the reason is a little bit technically complicated, but I will just summarize it very shortly. The reason is when you have red noise time series over the last 1,000 years. You calculate the principal components of the last 100 years. And that calculation will pick automatically at random those that are in sync over the last 100 years. For instance, those that show a common trend. It's just an artifact. By chance, they show a common trend. So the first principal component will pick those and take it as the first principal component of temperature. The problem is that when you go back in time, those series are not synchronized anymore in the past. They're only synchronized in the period in which the principal components were calculated. So they average out. And they produce, it was the original hockey stick, for instance, and random proxies, just red noise generated random proxies, will produce these temperature variations as well. So you cannot be sure. Is this an artifact now? Well, it would be plausible that it's an artifact. So the method, again, had these two flaws that were, in my view, fatal. And actually, the method has not been used anymore. It's a pity because, as I said, it was one of the iconic figures of the IPCC. Now, to be honest, other reconstructions based on newer methods will have some similar evolutions. Not a hockey stick, exactly. For instance, the reconstruction by Jan Esper using another method that was published 5 years later or so showed a much wider variations of temperature. But all of them, we have to be clear here, all of them show a very steep warming in the 20th century. So none of them uses reconstruct a flat temperature evolution over the whole millennium. Okay, I think well, we were very satisfied with the results. And this is a picture by Hans and myself that I think we came back from I infer from a very, very important meeting, because it's the only time that I've seen Hans with a tie. Probably I've worn that jacket twice. So it must have been a very important meeting, but I have forgotten which one. Nevertheless, we had a very nice time in the train, just talking about everything. Okay, now a couple of years later, this is a paper published in 2011. It was already a review about pseudo-proxy experiments. So you can imagine that this field evolved and expanded quite rapidly. And I have selected this sentence from the abstract. Well, I'm summarizing it. You can read that. For instance, the second sentence: pseudo-proxy experiments have established a common experimental framework. So now it's actually a routine that in all statistical climate reconstruction methods, and in other areas, for instance, also downscaling, estimation of future climate, you have to test your method with pseudo-proxy experiments. Otherwise, that would be difficult to publish. And another, very briefly, another evolution of this idea was the reconstruction of more realistic proxies. It was called the forward modeling of proxies. Instead of statistically generating these series that may look like tree rings that connected to temperature as they were tree rings, there are models of tree ring growth that take temperature, precipitation, and latitude, and radiation, and soil moisture from climate data, from climate model data, or from observations, and they produce synthetic tree rings. And they can be used perhaps more realistically to test reconstruction. Well, the conclusions. I have three conclusions here. The statistical models are necessary. So sometimes statistics really are pain, but when you're using a lot of data, they are necessary to interpret it. The second conclusion is a thorough testing with synthetic data is now well, widespread. It's just a must in every paper. And the third conclusion is that even simple statistical model, even linear regression with two variables, must be based on a physical reason. Otherwise, it can go wrong. And with these three conclusions and the last picture, then I would like to finish. And thank you very much for your attention.